Okay, hello and welcome back, everybody. Moving on to the second subsection, I suppose. Within the second section of this chapter, we're going to be discussing the exterior derivative today. And the exterior derivative, let's recall what we were studying in the last video, was the exterior product, or the wedge product. This is where you took two vectors and you were able to wedge them together. And we also studied differential forms, which were really wedge products of differentials, and we interpreted differentials as vectors. Of course, the exterior derivative is going to be the derivative which allows us to compute derivatives on differential forms. So for example, we'll consider differential forms today, something like xy squared dx plus xy dy, and we'll be able to compute a derivative of this differential form, but we'll have to do it in a very particular way. That's what the exterior derivative is going to be able to tell us how to do. So before we really get too much into the definition of the exterior derivative, which is what I have here, we start the definition just by talking about differential zero forms. And I just want to remind you, what are differential zero forms? These are scalar fields, or in other words, these are functions, multidimensional functions whose outputs are just one-dimensional. In other words, these look like functions of x1 through xn, whose output is a single expression involving the variables x1 through xn, right? We don't have kind of multiple outputs. There's only a single output there. So these are the zero forms, and we're going to start with the exterior derivative of a zero form. This is not going to be too much of a surprise. What do we expect the exterior derivative to be? Well, we start with an f. We denote the exterior by df. Surprise, surprise, this will be exactly the total derivative of that function, the total derivative we've been working with the entire semester. And so what have I written here? Here's df, and on the right hand side you can see I'm taking partial x in each entry. So these are the partial derivatives in each entry. Except instead of considering them inside of one giant matrix, normally you would think about the total derivative as one giant matrix. We're just going to assign each partial derivative that gets computed on our function to be the coefficient of its own differential, right? So these are all differentials in each respective direction. In other words, if this is a j on the subscript, that's a j on the differential. So let's just do one example of this really, really quick so we get an idea. Suppose I have f of x, y, z, and I'm going to let this be x, y squared, z cubed. If I want to take the exterior derivative, which is also the total differential, but kind of interpreted differently, we're going to do a partial derivative in the x variable of our expression. Of course, the partial derivative in x is just going to be y squared, z cubed, and then we multiply by the differential in that specific direction, so we multiply by dx. Then we have this summation here. We're going to sum over all possible of these directions that we can take partial derivatives in. So we're going to take a partial derivative now in the variable y, which will give us 2xy z cubed. We're going to multiply by the differential in that direction, so dy. And then we're finally going to add a partial derivative in the z direction. That's going to give me 3xy squared z squared. We're going to multiply by the differential in that direction, dz. It's very clear here what happened. We took a derivative of f, and you could think about it as the total derivative, and f started out as a zero form. What did we get when we took an exterior derivative? Well, these are actually an example of a one form, right? So the exterior derivative took us from a zero form into a one form. But once we have that idea of the exterior derivative on zero forms, it turns out we can now define the exterior derivative on any forms, any k forms, right? That's what we studied in the last video. So any sort of differential k form, we're going to take the exterior derivative basically by taking the exterior derivative of the coefficients of the k form. And I'll remind everyone what that looks like, right? Every k form is going to look like a collection of coefficients multiplying the actual wedge products of differentials. So here we have wedge products of differentials of k, right? There's going to be k of them when I have a k form, k differentials. And then, of course, we could potentially sum a lot of these together because we can have different choices of these wedge products, and hence each one will have its own coefficient. So how does that give us the ability to take an exterior derivative of a differential form now, something larger? Well, these collections of coefficients are actually just zero forms. So these are zero forms. And because we just decided how to compute the exterior derivative on zero forms, it turns out when we compute the exterior derivative on any form, we're just going to pass it directly onto the zero forms. So you compute the exterior derivative on any form, exterior derivative on a k form, it passes exactly onto the coefficients, passes directly to the coefficients, which were zero forms, right? Which were, not anymore, but they were zero forms. Well, now that we've taken a derivative of a zero form, we just saw when we started with the derivative of a zero form that you found out you got a one form out of it. So they were zero forms, and now these are one forms. And we just, since that's a one form, we're just going to take the wedge product with everything that's left over. So we're going to wedge it with everything that's left over. Now this last line is more of a specific way of showing how that would actually be computed. You really want to think about what I said in English rather than trying to decipher this last line here. So think about what I just came up with English, and we'll also do quite a few examples, and you'll start to see how this works. So really start to think about, if I'm going to take the exterior derivative of a k-form, we're just going to pass it onto the coefficients of that k-form, and then we're going to wedge that derivative against all the rest of the differentials. So let's look at an example here. We, of course, already worked with a zero form. Here's a zero form. If I'm going to take an exterior derivative of the zero form, I'm of course going to start by taking partial x of the zero form. In this case, that's 3x squared y squared z, and then I multiply by the differential in x. Then I'm going to take partial y of this zero form, which is 2x cubed yz, multiplied by the differential in y. Then I'm going to take partial z of this zero form, which is going to give me x cubed y squared, and I'm going to multiply by the differential in z. So we did see that right away. That's how we define the differential of zero forms. And then we'll step up and see how we take an exterior derivative of a one form. So here I've got a one form g, which would be x squared y dx plus xy squared dy. And if we remember what I said, if I'm going to take an exterior derivative here, then I just pass it onto the coefficients. So these are my two coefficients. I'm just going to pass the exterior derivative onto those two coefficients. And when I do, I will also have to include a wedge right after that, because that's going to make those coefficients into a one form. So I just pass it onto the coefficients and then wedge with everything else. But each of these coefficients is individually a zero form, and I already know how to take the exterior derivative of a zero form. So I'm going to go ahead and compute the exterior derivative of this zero form, which is just like what we started with earlier. I'm going to take a partial derivative in x of this, and I'm going to get 2xy. But I'm going to multiply by the differential in x, dx. And then I'm going to take a partial derivative in y, which is going to give me x squared, and I'm going to multiply by the differential of y, so I get dy. So that is all happening within these parentheses. And then when I started out, right, I paid the price when I was able to pass my exterior derivative onto the coefficients. I paid the price of a wedge, and so that wedge is still here. The wedge is happening after the parentheses where the exterior derivative is. So we're going to do the same thing on this second entry, which I've included with the exterior derivative and a wedge. Now when I take the exterior derivative of that zero form, I'm going to be taking partial x, which is just going to give me y squared. I'm going to multiply by the differential in x, and then partial y, which is going to give me 2xy, and I'm going to multiply by the differential in y. And I do still have to account for this wedge afterwards, so I still have the wedge afterwards. At this point, we're technically done. I'm going to put that in quotes though, so technically finished. Technically finished. Except there's a lot of simplification we could do. So at this point, we can think about, yeah, wedge products truly are products. And so what do products do? Products distribute. So this wedge product will distribute, this wedge product will distribute. And what I'm left with then is 2xy dx wedge dx. Here we go. 2xy dx wedge dx. X squared dy wedge dx. So here's x squared dy wedge dx. I'm left with a y squared dx wedge dy. Y squared dx wedge dy. And I'm left with a 2xy dy wedge dy. So 2xy dy wedge dy. And then one step farther, we can remind ourselves that wedge products, when they see vectors wedged with themselves, the wedge product is always zero, right? So in this dx case or dy case, the wedge product will always be zero. And so all I'm left with is actually these terms, which have a dy dx and a dx dy. And I could once again be finished technically, or I can remember that wedge products are alternating. And so by remembering that they're alternating, we remember dx wedge dy is negative dy wedge dx, or vice versa. And so I can go ahead and just exchange the order of dy dx at the cost of a minus sign. That's going to give me a minus sign on the x squared term. So then I can actually combine the x squared and the y squared into a y squared minus x squared, multiplying dx wedge dy. And so that's really the most simplified version of the exterior derivative of this particular differential form. I'll go through one more example here where I can work with a differential 2 form from the very beginning. Right, so here's my differential 2 form, y squared z dx wedge dy plus z squared x dy wedge dz plus x squared y dz wedge dx. And if I'm going to compute the exterior derivative on h, remember I can just distribute it to the coefficients of each of these terms alone. So I'm going to distribute that exterior derivative to those coefficients, and I pay the price of a wedge against each of the coefficients. But now that I've distributed to each coefficient and paid the price of a wedge, I once again am just thinking about that as the exterior derivative of 0 form. This is the exterior derivative of 0 form. This is the exterior derivative of 0 form. And I'm just going to expand each of them out. So in the case of dy squared z, I of course have, well, I have a partial x on y squared z, but partial x is 0. So there really should be a 0 dx here, but I haven't included it because, of course, 0. And then I have partial y, which is going to give me 2yz, and then multiply by the differential in the y direction. And then I have a partial z, which is going to give me y squared, multiplied by the differential in the z direction. I'm going to do the same thing with d of z squared x. I'll have a partial x on that, which will give me z squared dx, and I'll have a partial z on that, which will give me 2zx dz. There's technically a partial y there as well, but just as before, the derivative in the dy direction will just be 0, so I don't really need to include it. I'll then finish with the third term here, d of x squared y, and the outcome there is going to be partial x, which is 2xy dx, and partial y, which will give me x squared dy. If it's starting to look familiar, going all the way back to Calculus 1, each of these computations is actually somewhat related to implicit differentiation, right? In some sense, we're seeing implicit differentiation of these variables if you like to think about it that way better. It's all kind of the same calculus, and of course that should make sense, as math doesn't actually change as much as you might expect. But this is, can be considered implicit differentiation of the variables, or the exterior derivative, or the total derivative of multivariable calculus. It's all kind of the same math. Well, anyway, once I've computed those exterior derivatives, I've got each of these differential forms that all have wedges between what I just computed and their original differential forms. And so what we're going to do, as before, is we're going to take this form and distribute it along with a wedge to both of the terms out front. We're going to take this differential form, distribute it with the wedge to both terms out front, and this one distributed with the wedge to both terms out front. What that's going to give me, of course, is a 2yx dy dx dy. Then I'll have a y squared dz dx dy, so y squared dz dx dy in that first line. I'll have a 2zx dz distributed against a wedge, dy wedge dz, so dz wedge dy wedge dz with a coefficient 2zx. Then I'll have a z squared dx wedge dy wedge dz, z squared dx wedge dy wedge dz. And then for the last line, I'll have a 2xy dx wedge dz wedge dx, 2xy dx wedge dz wedge dx, and an x squared dy wedge dz wedge dx, x squared dy wedge dz wedge dx. Kind of as before, in fact, either of these are technically finished, but there really is a lot of simplification we can do. Not only can we distribute, but we start to notice anytime we have a dy dy, anytime we have a dz dz, anytime we have a dx dx, wedge products, every time that you have two copies of a single vector in a wedge product, they have to give you 0. Right? Two copies of any vector in any wedge product will give you 0, and so all of those cancel. And we should also notice now this is dz dx dy, dx dy dz, dy dz dx. They're all kind of versions of the same wedge product. If we start to exchange terms around, we just have to pay the price of some plus and minus signs. So in fact, we can combine everything together. I've kind of shown everything here that we have 3 copies of 0, and we can also rearrange dz dx dy. All we have to do is we have to pull dz over once and then dz over again to get it in dx dy dz form. Of course, since I pulled it over once and then twice, I really have a -1 squared out front, but -1 squared is just 1. In the second case, I need to take this dx and pull it out front twice. And that will give me dx dy dz, also with the -1 squared, equals 1 out front. And so making those rearrangements, what we actually have is we can rearrange each of these into dx dy dz at the cost of nothing, and we'll just get x squared plus y squared plus z squared against dx dy dz in this situation. Since we can compute exterior derivatives, you might ask the question, can you take second derivatives, right? We can normally take second derivatives in calculus. We should be able to take second derivatives of exterior derivatives. Well, let's find out. So let's take this first example we had of our first exterior derivative above. That's just a 0 form, and so its first derivative is just going to be a 1 form, which I have here. And let's go ahead and compute one more derivative of this particular 1 form. Well, the way we're going to do it take d on both sides, but of course I know I can just pass it to each of the coefficients at the cost of a wedge. So I'll put a d on that coefficient at the cost of a wedge, and a d on that coefficient at the cost of a wedge. And now I'm just going to compute the exterior derivative of each of these coefficients individually. And we've been doing it a lot right now, so I'm going to pass it through pretty quick. If I take the exterior derivative on this first coefficient, we're going to get 6xy squared z dx plus 6x squared y z dy plus 3x squared y squared dz. If I take the exterior derivative of the second coefficient, I'm going to get 6x squared y z dx plus 2x cubed z dy plus 2x cubed y dz. If we take the exterior derivative of the third coefficient, we're going to get 3x squared y squared dx plus 2x cubed y dy. Now, the reason I went through those so fast is because it's actually not important. I mean, it is important, obviously, the computation, but that's not what I'm trying to stress with this example. You'll see what I'm trying to stress later. We've gone ahead and computed this exterior derivative on each coefficient. We can now actually perform the distribution of these remaining wedges against each of the terms in the exterior derivative of each coefficient. So if I pass those wedges across, we see what we have here. And it's not super important that you necessarily agree with me what we have here right now. What's important is I'm going to start to simplify this. Okay, so when I start to simplify this, we recall every case where we have dx wedge dx or dy wedge dy, those cases will necessarily disappear. In every other case, we can flip things around at the cost of a minus sign. So let me show you, if I take my dy dx term and I find the other dx dy term, let's just flip this around at the cost of a minus sign on the coefficient. Now observe that coefficient and this coefficient. What we're observing is that the one is exactly the negative of the other, and so these coefficients exactly cancel. So now those terms are gone. If I look at my dz dx wedge and my dx dz wedge, well, I can swap the dz, the dx, at the cost of a minus sign. And now I look at the coefficients, and the coefficient here is exactly the negative of the coefficient here, and so just as well, these are going to cancel. And I'm only left with one term, dz dy and dy dz, and at the cost of a minus sign, I can flip the dz dy, put a minus there, and what do you know? These are exactly opposites of one another, and so these will cancel as well. And actually, you know this. You know these all have to be the opposite of one another. This is the Schwarz lemma that's telling you partial x, partial y equals partial y, partial x. That's normal on its surface, but each of these is associated in the left side case is going to be the coefficient of something like dx wedge dy, and on the right hand case is going to be the coefficient of dy wedge dx. And because flipping them around incurs only a minus sign, right? You'll incur a minus sign for flipping them around. You're always going to end up with one positive version of this and one negative version of this in your second exterior derivative, meaning the second exterior derivative will always give you 0, 0, 0. It's always going to be equal to 0. In fact, this will stay the same no matter what the k form is. So in this case, let's say I start with a 1 form, so now my exterior derivative is a 2 form, and let's go ahead and compute one more exterior derivative of our 2 form. If I compute one more exterior derivative, put a d out front here, all I have to do is put a d on the coefficient term at the cost of a wedge, and the d on the coefficient term here, dy squared minus x squared, will of course give me 2y dy minus 2x dx, and then wedging against dx dy. Of course, what do we have here? We've got a dy wedge dx dy, but there's two y's in that differential, meaning dy wedge dy is 0 as always, and there's going to be 2 x's in this differential. Dx wedge dx is going to be 0 as always, and so we find out again that the second derivative of any differential form will be 0. And this is actually true no matter how you decide to do it. I've got another case here where we have the exterior derivative of starting out with a 2 form, and then of course the exterior derivative of 2 form is a 3 form, and suppose we take an exterior derivative of this 3 form, we are actually going to end up with 0 yet again in every single case. And so we have this lovely lemma, this is part 1 of our lemma actually, called Poincaré's lemma. And Poincaré's lemma is telling us in part 1 that the second exterior derivative of any differential form will necessarily be 0. Now this might feel confusing because second derivatives in terms of multivariable calculus are not necessarily equal to 0. This is specific to differential forms, to exterior derivatives and differential forms, specifically because of the way the wedge product works, specifically because of how a wedge product is computed. So you can't necessarily say that, second derivatives of regular multivariable functions are equal to 0. That's not really true. The second total derivative, we use the second total derivative in the Taylor series in some other cases, the Hessian matrix, for example. So that's not necessarily true. But when we ascribe the extra meaning to it, when we're using an exterior derivative instead of a regular multidimensional derivative, we do have to get 0 as the output of the second exterior derivative. Now that gets confusing, right? Because that can sometimes mean the second total derivative and sometimes mean the second exterior derivative. So I do want to point out right now, you must use context clues or verify in some other manner when you are asked for the derivative d if it refers to the total or your multivariable derivative or the exterior derivative. I've definitely been confused a few times in my life seeing d squared and thinking it means the total derivative squared, which kind of produces the Hessian matrix or similar computations, and it's actually been the exterior derivative or vice versa. So you do have to use context clues or ask somebody what they're referring to in a lot of these cases if they're referring to the exterior derivative or the total multivariable derivative. It's nice that they agree from 0 forms to 1 forms, they agree. It's the same computation, but in any higher order forms, they're going to disagree, so you have to be a little bit careful there. Usually context clues can get you there. Anyway, in terms of exterior derivatives, the second exterior derivative of any differential form will always be 0. And I do have a nice proof here, but I'm not going to go through the proof. You can look at the proof if you would like to. It just corresponds to making sure that you alternate your products correctly and then use that Schwarz's lemma. And so in many ways, that does conclude the topic of the day, the exterior derivative. But I do have this really lovely remark at the end of the section that I do want to go through because I think there's lots of fascinating things happening in this remark, really going to tie the entire semester together so far. And so this remark is stating that the gradient, the divergence, and the curl, 3 versions of the derivative that we've been using this semester, are all actually special cases of the exterior derivative. So some way this exterior derivative is unifying many of our notions of derivatives. We just saw it doesn't really unify higher order derivatives because the d squared is going to be different in exterior derivative world, but it does unify at the very least these 3 ideas, which somewhat felt related already, right? They all kind of rely on this operator, either the gradient as an operator, the divergence, or the curl as an operator. But it's very interesting to see that they're all special cases of the exterior derivative. So let's see exactly how that works, and we're going to start with the gradient. So let's just start with the gradient, and this one shouldn't be much of a surprise. If I just compute the exterior derivative of a 0 form, and recall that a 0 form is a scalar field, well, the exterior derivative of 0 form is, of course, just partial x1 on that form times the differential x1, partial x2 on that 0 form times the differential x2, all the way up to partial xn of our 0 form times the differential xn. But now if we remember that each of these differentials, they really are themselves vectors, like dx1 would be 1, 0, 0 all the way down to 0, dx2 would be 0, 1, 0 all the way down to 0, and dxn would be 0, 0, 0 all the way down, and then eventually a 1 at the end. Right? These are all different vectors. And now what we have here is a linear combination of vectors where the coefficient of each vector is the partial derivative. And of course, if I add all of those partial derivatives in different rows of the vector together, we're just going to get a giant vector comprised of partial derivatives. Now, what I've done at this subscript here, I'm just kind of specifying that, yeah, the coefficient, these are all coefficients specifically for which vectors. They're coefficients for dx1 and then dx2 and then eventually dxn. That's one way of notating kind of the basis set for a vector. But what is this vector now? This vector is exactly the gradient, right? So we see that the gradient just shows up as the exterior derivative of any sort of 0 form, as long as you ascribe these differentials as the basis set that the gradient exists for. So that's kind of the easiest situation where the gradient is the special case of an exterior derivative. Now, this second case is going to be a little bit more complicated. It is actually quite more complicated. It's not great, but we're going to see where the divergence comes from. So suppose we have an n-1 form embedded in an overall space of n, right? And so we're thinking, hey, if we are in R3, suppose we have a 2 form, right? 2 form in R3, a 3 form in R4, a 27 form in R28. Hopefully you get the picture. The number on the form is 1 fewer than the total number of dimension. So let's interpret that n-1 form as a vector field with basis elements given here. These are, of course, exactly the differential elements of an n-1 form. Okay, but I've actually specified their order very specifically. So how is the order going to work? Well, I'm stepping up, or I'm starting at j equals 1 up to n. So it's like, this would be like e, so e1, for example, I'm just not going to use that subscript, so I'm not going to use 1, and then I'm going to write out, well, -1 to the 1 minus 1 up top. I'm just going to write out, this would be dx2 wedge dx3 wedge dot 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 wedge dx to the n. And then e2, I'm just going to omit the dx2 term from it. So then I'm going to have, well, I do have to pay the price of this -1 out front. So I'll have like negative dx1 wedge dx3, right? So e2 avoids the superscript 3. Then you have wedge dx4 dot 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 wedge dxn and so on dot 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 en. You call this one -1 to the n minus 1, and then you have dx1 wedge dx2 wedge dot 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 wedge. Well, it stops at n minus 1 in that case because you're omitting the n from that wedge. So because I've omitted exactly one entry from all of these wedges, that's what makes them all an n minus 1 form, right? These are all n minus 1 total terms because I've omitted exactly this this subscript on my basis vectors. Not really a big deal that you understand that. It's just more important that I do bring it up in this case because we're going to see how the divergence is special. So suppose I've assigned the vector field, which corresponds to this n minus 1 form, specifically these basis vectors. If I do it that way, well, then you can represent the n minus 1 form as this object. And when you take the exterior derivative of that object, if I take the exterior derivative of this object, of course, the exterior derivative just happens to go on the coefficients, and I pay the price of the wedge product. And so that's what we see here. It's the derivative on the coefficients, wedge the rest of the terms. But what happens in this case, if you write out, what would this be? Well, it would have to be, right, the exterior derivative of any zero form is just the sum of the partial derivatives, partial xj of fi of x, and then dxj here, right? So that's going to be those terms. That's going to get wedged with ei. Well, what do we know? Anytime that xj, dxj shows up somewhere in here, anytime it shows up in our basis elements, I know that that term has to be 0 because of the way the wedge product exists. So it turns out the only terms that survive this operation, the only terms that survive the operation are exactly the terms that have partial xi, because we specifically omitted the I differential from that specific E. And so that one survives. You get a dxi wedge ei. And in fact, you have a sum of all these because you can sum from I equals 1 to n. And now what happens is that all of these wedges contain exactly one copy of each direction. They contain exactly one copy of each direction, so they can all be rearranged into some version of the ordered dx1, wedge dx2, wedge dx3, all the way up to the top. And we've chosen those coefficients, these -1s, to alternate in such a way that they exactly cancel with everything. And so what we pick up here is that this sum right here exactly becomes the single coefficient of the single very large wedge term that's out at the end there. And so what you get here, this is actually a one-dimensional, this is in a one-dimensional vector space. And the sole coefficient in that space happens to be precisely, well, it's the sum of all the partial derivatives of each entry of f individually. That's exactly the divergence. The sole coefficient is the divergence. So that's kind of cool. You can get the divergence out of this. You have to be, this feels a little contrived, I understand. But there is good ways of actually thinking about the divergence truly as this object, even though it feels contrived. And finally, we can find the curl, but let's recall the curl only exists in 3 dimensions. And so let's start out with a one form in 3 dimensions, and this one form is going to look like fx of xyz plus fy of xyz dy plus fz of xyz dz, right? So fx is the coefficient of dx, fy is the coefficient of dy, fz is the coefficient of dz. Of course, if you think about dx as 1, 0, 0 in the cotangent space, dy as 0, 1, 0 in the cotangent space, and dz as 0, 0, 1 in the cotangent space, what do you actually get out of this? You just get the vector fx, fy, fz. And if we go ahead and actually compute an exterior derivative of this, well, we can pass it to each of the coefficients individually at the cost of a wedge, and a wedge. And when I do that, well, I'm going to take a exterior derivative of fx, which will include a partial x on here, but of course that term disappears because it's just dx wedge dx. And then I'll have a partial y on fx and a partial z on fx. I will also have on the middle term a partial x on fy, a partial y on fy, but that disappears because you have a dy wedge dy. You'll have a partial z on fy. And then we'll also take the exterior derivative of the third entry of f, which will be partial x on fz, partial y on fz, and partial z on fz, but that term will be 0 because we have the wedge of dz with dz. And so the terms that survive, we really have this term, which is the dy dx term, and we have this term, which is the dx dy term. We can add those together. We have this term, which is the dz dx term, and this term, which is the dz dx term, and add those together. And we also have this term, which is the dz dy term, and this term, which is the dz dy term. We can add those together, up to some minus signs to make sure that the differentials on the edge actually align. Well, when we include those minus signs, what do we actually see as our three entries? We see partial y fz minus partial z fy. We see partial z fx minus partial x fz, and we see partial x fy minus partial y fx. If we ascribe this differential form dy wedge dz as our first basis vector, if we ascribe dz wedge dx as our second basis vector, and if we ascribe dx wedge dy as our third basis vector, then we just combine each of these terms into one giant vector. And what do we get out of this vector? It's exactly what you would expect. We get the curl of f. You're exactly getting the curl of f as our three entries in this vector. Okay, anyway, that's what I wanted to cover today. I think it's pretty cool that you can see all of these curl, divergence, and gradient show up as specific exterior derivatives. That part won't really be tested on. It's really going to be a question of, can you compute exterior derivatives of really any differential forms? And do you remember that? I guess I'll point it out again. D squared of f is equal to 0 as long as you interpret that d squared as an exterior derivative. All right, that's where I'm going to end. We're going to talk about primitives and closed and exact forms in the next video. See you then. Bye.